Okay, so we know how to make trans diols. And so the question is, how do you make cis diols? And that means syn hydroxylation. Syn meaning they're going to add together on the same side. So to do that, for my alkene, I'm going to use osmium tetroxide, and I'm going to use hydrogen peroxide. So once you form your osmium ester, then what you're going to do is you're going to do a redox reaction to form your final diol on the syn side. Another set of reagents you can use would be potassium permanganate. And you want this to be dilute and cold because you're going to see we're going to use potassium permanganate for more rigorous reactions as we move forward with alkenes and alkynes. But for potassium permanganate, it's dilute cold, and you want it neutral, or you can have some hydroxide in there. You're going to form your diol. Okay, and in fact, we're familiar with this because we use this when we were testing for your alkenes, because the brown precipitate is in your redox reaction, manganese dioxide, and this is a brown precipitate. Okay, so not only do you use it for a reaction to form your diols, but you can also use it to test for the presence of alkenes. All right, so let's go on and let me just show you what the esters look like before we get our diol. So with my osmium tetroxide, okay, what happens is basically you form, attacks the oxygen, this goes up into osmium, and that attacks the carbon. So this is my osmium. So this is the ester, okay, that you're going to use, which then, upon addition of hydrogen peroxide, gives you your diol. Okay, so that's what you're going to look at. It's called an osmate ester. Okay, likewise, potassium permanganate works similarly. So with potassium permanganate, we'll start with the ester form. Okay, is that you have again your alkene, okay, and then basically again this, just with an orange, sorry. The blue bond attacks this, that goes there, that goes there, form is your manganate ester, right? Okay, and this is what, when you add your hydroxide. Okay, that continues on. It can be neutral, or you can add your hydroxide, but that's what's going to end up. You're moving your manganate, and that's how you get MnO2. Okay? Alright, so those are two ways to form your diols that are in the syn orientation. So, let's take a break. Okay, let's just do a quick review on some of the reactions we learned before we finish off reactions on alkenes and move on to alkynes. So, we have an alkene here, and what we're going to do is, under these conditions, this is alpha elimination. So we're going to form a carbene. And because this is a meso compound, we don't form any enantiomer. That's all we're going to form. What happens if we form an epoxide? Likewise, with MCPBA being concerted, okay, we're just going to form this. There's no enantiomer. However, I want you to note that when we draw our products, make sure you indicate cis, because that's the type of product you're going to get. If you draw just straight lines, that indicates you can get cis or trans. And as you know, because of the stereochemistry, the cis isomer that we started with, we're going to have the same thing, the cis orientation on our carbene, our cyclopropane now, and our epoxide. Likewise, when we do make the halohydrin, and then we do the sodium hydroxide, that means we're going to get a ring opening to form the trans diol. Do I have to worry about the regioselectivity? Because I have both are going to become the same type of carbocation. It's going to occur on both sides. This is a chiral compound. So make sure you write plus enantiomer. Okay? If we do this one, this is making a carbenoid. That's my Simmons-Smith. And finally, this is doing the syn hydroxylation, making the diol. And as you can see, this is meso, so we don't have to worry about saying plus enantiomer. Okay, so now let's continue on with the rest of our alkene chemistry. Okay, so let's move on to the cleavage of alkenes, the cleavage of this double bond. There are two different types of reagents that we can use. The first one that we're going to talk about is the use of potassium permanganate. And we already saw the use of potassium permanganate, where it will add across a double bond to form my diol by doing syn hydroxylation. What happens is if you use warm concentrated potassium permanganate, it forms the diol first and then it'll continue to oxidize, so that cleavage of this double bond, you continue to oxidize your alcohols, and then if these are all R groups, you'll get ketones. The key is to have your carbon double bonded oxygen here. Now, if you have on one side a hydrogen, then what you form initially is an aldehyde, but then that continues to to get oxidized by my potassium permanganate to give me a carboxylic acid. Okay? If I have a terminal alkene, so I have a CH2 here, then again you form your aldehyde. It continues to get oxidized by potassium permanganate, gives you formic acid, and the formic acid continues to get oxidized, and that's how we get my carbon dioxide and water. Okay, let me show you the next way we can cleave alkenes, and that's with ozonolysis. Okay, now when we talk about ozonolysis, the first step is basically to use ozone. After you do that, the second step, we use dimethyl sulfide. And the reason we use dimethyl sulfide is that's a reducing agent. So what you get is you get cleavage of my alkene. Now, why is the second step, using dimethyl sulfide, of significance? If I cleave this and I have a hydrogen here, because this is a reducing agent, it does not continue to oxidize past my aldehyde stage. So I do not get a carboxylic acid. I stay at the aldehyde. If I have my terminal alkene, then you'll get your ketone and you'll stop at formaldehyde. Okay? So what we'll do is we'll do a few examples. Let me show you first, before I give you some problems, how we can do structure determination with this. Suppose you had some unknown compound and you subject it to, let's say, potassium permanganate that's warm and concentrated. Okay? And you get something like yes. Okay. So the question is, what is my unknown compound? Okay. So some of the things that you can consider here is this: 1, 2, 3, 4, 5, 6. 5 and 6 membered rings, remember? Are very stable. So you're more likely to get a 6-membered ring than to get a 12-membered ring if I use 2 of these. So then I say, okay, so let's say let's work backwards. If I work backwards and say I have a 6-membered ring, and this is my alkene, then I have a methyl group here. And I have a hydrogen here. Okay, so if I break this with my potassium permanganate, I would get an oxygen there, and since I have a hydrogen, it becomes my carboxylic acid. Then 1, 2, 3, 4, right? 1, 2, 3, 4. And then now I'm cleaving here. I get another carbonyl group and then CH3. Okay. So what that means is that this allows me, you see that? Let's double check, to work backwards to get my original compound. So this is the same thing. This is in the linear form. If I put it around, I can see this is where I have my double bond. And I put it back together. So my original structure must have been this. Okay, let's try a different one. Suppose I have a compound here, and I subject it to ozonolysis and then dimethyl sulfide. And what I get is 2 moles of acetaldehyde. Okay? So, what was my original structure? Right? So, whatever I had has 2 of these units. So if we work on that, we know when I do the cleavage, this is part of my double bond. So this is 1 mole. This must be my other mole. Okay? So you know you must have come from a compound like this. Is that the only compound? And the answer is no, because you could also have had this orientation. So if I say what was my original compound, it's going to be CH3, my cis 2-butene, and it could be a mix, or my trans 2-butene. Okay, so by knowing what our products are, we can determine what our initial reactant is by using ozonolysis as a tool for structure determination, or using potassium permanganate. Okay, now we're going to move on to start looking at polymers. We'll quickly talk about polymers and metathesis. Okay, so let's talk about polymerization. And remember, a polymer is a very large molecule that's made of a series of monomers. So in this case, a polymer, we're not talking about 2 or 3, we're talking about hundreds to thousands to tens of thousands. Okay, so this unit here is called a monomer. Well, where did this unit come from? This unit came from isobutylene. Now, when we talk about polymerization for alkenes, alkenes tend to undergo what we call addition polymers or chain growth polymers, polymerization. And what you're doing is you start off with your unit, you just add on one at a time. Okay, so let's go through. There are 2 types that we're going to talk about. We're going to talk about cationic polymerization and then free radical polymerization. So the cationic polymerization, you have something to initiate it, like sulfuric acid. You have an acid. And what you do is, let me just put the H plus here. I use a different color. Okay. What you do is you have your acid, and it reacts with your first unit. And when it does, what happens? It it's protonated. And this being an electrophile, you're going to have to get the most stable carbocation. So this carbon will carry the positive charge. Now, since we're in a huge pot full of isobutylene, then what happens is it adds on another isobutylene, and when that happens, I now have a dimer. Here's my first unit. Here's my second unit. Okay? And then with another isobutylene, I'll form my trimer. And this just continues to grow until you get a very long chain. And that is how you get a cationic polymerization and how that works. Okay? Get your large chain growth molecule. Alright, so let's do the next one for polymerization. And the next one for polymerization is going to be free radical polymerization. Again, it is a chain growth. It is an addition polymerization, but instead of using a cation, we're going to go through a free radical mechanism. So, what you need to do free radical polymerization is one, you need an initiator. Oftentimes what we use is a peroxide. Okay, so ROOR with heat give us two radicals. Okay, so now the second one, we're going to be focusing again on propagation, which you guys probably know inside and out by now. And with propagation, let's take a look what happens. So if I take something like styrene, okay, and I have a free radical, okay, what's going to happen here is one of my electrons forms a bond with my initiator, and then I get a radical there. Okay, so I have a radical here, and OR here. Okay, so now this free radical can react with another styrene. Do this here. I'm going to flip it around just a moment. Okay, so this one is this. Okay, so I have that OR. Okay, so I just turn this around. Okay, now this new bond is here, goes to that end, right? So it's like here. So this one to this carbon, this one is that carbon, and you just draw it out, make it a little prettier. Stage 2, radical, right there. So 1,2-phenyl, 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 1,2-phenyl. Okay, and you can see that it can continue. So again, I'm going to just draw this in reverse. I apologize. Well, I don't even like my drawing here. Okay, this forms a bond here, form a radical there, and now I have my initiator and my first. This is my first styrene. This is what I made my second styrene. Yeah, okay. This is my trimer, and I have a radical here, and this continues to propagate. Okay, and so for this one, this is how we get polystyrene. Okay, so polystyrene is made from free radical polymerization, and polyisobutylene is made from cationic polymerization. Right? So do we have an anionic polymerization? Yes, we do, but not for alkenes. So when we get to that point, we'll talk about it. And when we do draw this structure, oftentimes when you see us draw structures of polymers, okay, you'll see a bracket, okay, and it'll be like a CH2, okay, CH2-phenyl. You might just kind of draw a couple so you can see the pattern. So CH2, CH2-phenyl, 1, 2, CH, excuse me, okay. All right, and then I have here CH2. Let me just make sure I get my, here's my chain. Better make sure I get my chain right. So let's say CH2, and then I have a CH, phenyl, CH2, CH, phenyl, and then we draw an N. So that tells us that we have a large number of these, and that I take this and I just repeat it. Okay, so sometimes we'll do it this way, or sometimes you'll just see a single unit, so you know what our monomer is. Okay? Alright, so let's move on to metathesis. And we won't spend a lot of time, but you should know what metathesis is. It's gained a lot of headway in organic chemistry because of its versatility. Okay, so let me just tell you what it is and give you an example. Okay, olefin metathesis. So basically, all we're saying, suppose you have an alkene here, and you have an alkene here. And all we're doing in metathesis, you have your catalyst, okay, is that you're forming two this should be trans. Okay. You're going to be forming two of these types of alkenes. And all you're doing here is this. You're cleaving this bond. You're cleaving this bond. And you're forming a new alkene here. And you're forming a new alkene there. So that is what an olefin metathesis is. Okay. So let me just give you give you an example. Okay? So, the types of catalysts you use is really key here. You have the Schrock. Oh, I can't even spell Schrock's name. Okay, we have Grubbs. Okay, and Robert Grubbs. He's retired now. So Schrock has molybdenum. Let me give you... Oh, I'll go ahead and show you. It's... Okay. Oops, sorry. Okay. Please don't memorize this. Okay, this is just an example of what I'm talking about, that's all. CF3. Okay. And there's one more. Okay, so that's when we talked about the catalyst. This is a Schrock catalyst. Okay. So he focused on molybdenum. Grubbs focus on rubidium. So we're talking about a lot of organometallic work. So Grubbs. What's interesting about these, and we'll talk about what happens here. Cyclohexane H10, 12, 12, 11. I'm going to just do it this way. Cyclohexane. Cyclo. Oh my goodness. Cyclohexane. We have 3 of those rings here, and we have 3 of these rings here. Okay. Now, here's the important part. When you look at these catalysts, and we're thinking about the double bond, you cross your olefin metathesis. This will be the exchange, the alkene on one of your compounds. That'll be the alkene that you break, and this will be what gets exchanged for the other one. All right, so let's go through and just give you a couple examples of types of usefulness for olefin metatheses, and then we'll stop. All right, so if you look at an example like this, what you get, okay, with your catalyst, all right, six. This is called a cross metathesis. Okay, here, here. So we have these two. It's almost like a double displacement, right? A, B, C, D. So you get AD, and then CB, right? You can do the same thing. 2, 3, 4, 5. Okay. So, if you put in your catalyst, then basically you would get 1, 2, 3, 4, 5, 6, 7. Okay, so you can do a cross metathesis where now you've exchanged this half and that goes together and this goes with that. So 1, 2, 3, 4, 5, 6, 7, 8, 9 minus 2. 1, 2, 3, 4, 5, 6, 7. And my ethylene. That's ring closing. So we can, that's a triple drawing. Let me just redraw the 7. 1, 2, 3, 4, 5, 6, 7. That's still not perfect, is it? Okay. But as you can see, you can use cross metathesis, or you can use olefin metathesis as a whole to do ring closure. Okay? And you can do ring opening. Okay? So why is this important? Because what happens is it was for polymerization. So let me give you the Norbornian example. This is called Norbornian. I'm going to use my catalyst. Okay? What's going to happen is you open up your ring. Okay? Good. Let me see if I can draw this right. 1, 2. Yeah. 2, 3, 4, 5. Is that bond? 1, 2, 3, 4, 5. Okay. So what's happened here is you're going to get polymerization. Okay. So how did that work? Let me just. Okay. So if I take 2 of these, remember I'm going to exchange right here. Let me just show you what happens with 2 of them, and you'll get a better feeling for it. I'm going to if you know, I'm going to cleave right here. Okay? So I'm going to have to form a double bond on this side. I'm going to form a double bond on that side. So you can see this is my 5-membered ring, which goes right there. So I have my 5-membered ring, and I have a double bond, and on this side I have a double bond. Okay? Now what is it double bonding to? So remember what I'm doing is this. If I said, remember how we were talking about A and H's? So this is A, and H here, and H here. And this is B, and H, and H. Then what you form, remember, exchange it. So you said we get A, B, H, H, right? So what are we doing here? We get A, which leads to my 5-membered ring. Okay, and this one goes somewhere, right? And then we get the B, right? It should be here, right? The B and the H, and B is my 5-membered ring. Okay, and then this continues on. So you can see that here is my ring, here's my double bond, here's my double bond, and then again I get my ring and I have a double bond and it continues. So when you use something like Norton boring, you can also get a metathesis polymerization. I think this one is the same as the others. It's just a little hard to see because when we draw it, here's my 5-membered ring. It's right here. So having the rings can be confusing. Just kind of number it and follow the chain through. And you can see how it's been formed. Okay, so that's our reactions for alkenes. We'll do a summary next and start moving into alkynes.